Hi, my name is Reese Brown, and this presentation is on ROS framework in harvesting fruit robots. So let's begin. So some of the issues with harvesting robots currently is actually harvesting dense crops, as it can actually get quite a few false positives as there's too much interference. This can actually provide a low yield rate for actually picking up fruit. And also this, when processing so much data, can lengthen execution times. Another issue is where it's so dense as well, the movement of the robotic arm within these areas can knock fruit down, also reducing the yield rate within this actual area. So iron hand in conjunction with visual serving is actually a really good method in general, and is mainly used in currently fruit picking robots. So reason why is it can do a constant feedback loop as it continually updates the end effector, so adjusting to new positioning. Another aspect is it also has something called multi-approach or single approach. This will be talked about a lot later in the presentation, but it is, well, can be used in humanoid robotics as well. Second reason is this is actually quite a cheap system as you only just need one camera compared to multiple cameras, and you can, well, it's very adaptable. And over time, you can train it to a very high degree and can do quite a lot of things as like fruit detection, which we're talking about, and many others. So in the main case study that we've been looking into, it already has a ROS framework. So this is pretty much six nodes talking to each other. So you have got robot control, fruit detection, image acquisition, visual servo control, SLAM, and application control. So we'll be talking about each one of these nodes, their functions, and how they all overall interact with each other. Um, some of these information is actually taken off a sweet pepper harvesting case study as well. This is where goes more into the actual visual servo control and the iron hand method. So overall, we'll be breaking down this whole aspect of this case study. So SLAM stands for simultaneous localization and mapping. So what this is actually normally used in is automation vehicles. What it does, it pretty much builds a 3D representation of the world, mapping it out so uh, the vehicle or robot or whatever it's attached to understands its location within the world. So they do this by either using cameras or LiDAR. In this case study, they use cameras instead of LiDAR. But in this case study, they don't use normal SLAM, they use something called LSD SLAM, also known as large scale direction SLAM. So the difference between this and the normal SLAM is this actually runs in real time on modern CPUs. It can actually run on your smartphone, a Raspberry Pi, anything with a camera and a small computer. So what it does, it just takes images from a camera, it doesn't use LiDAR, and it processes it into what you see here on the image, more like outlines of an area. Great thing about this already is there's actually a library already in ROS, so you don't actually have to code it all up yourself. It's existing. It's nice and easy for anybody to do. So the goal of fruit detection is to provide information about a fruit in a given image. So is it ripe enough for picking and what fruit it is? The issue of this is depending on the weather and the luminosity of the area, this can actually affect the imagery of the image. So it might actually be a pear, but for some reason it's picking up as a green apple. So one way to combat this in multiple case studies they actually use is something called a C-Labs color space. This method is actually used in actually by photographers, funny enough. So what it does, it takes all the noise and provides a more of a clearer image of what it should be. Um, so this is done by having three inputs. A and B is basically the coloring. It allows you to adjust the coloring of an image. Third input is luminosity, represented as L. That allows you to change the brightness, and in general, you can tweak these around to get your desired output. Um, but in this fruit detection node, they didn't really care about the ripeness or anything. They just wanted to tell what's red peppers from a green background. What they did is they applied a advanced blot detection algorithm. So what is the fruit really there? And then they converted that into C-Lab color space. and all they did was return the findings back to the applied control node. So the image acquisition node is really simple. What it does, it just takes an image and sends it to whatever node requires it. So if fruit detection says, "Oi, I need an image," image acquisition will take that image, process it by removing lens distortion, and then sends that image to fruit detection so it can, well, do what it needs to do there. Really simple and easy. So the robot control node provides the functionality to move the endpoint of a robot to a desired positioning. So it receives real-world Cartesian coordinates and returns a movement status. So with the visual servo control updating, which updates the end effector multiple times per second, it could do closed feedback control with this quite easily. All this does is takes information or data from visual servoing and then translates it into movement for the robot itself. So the visual servoing control node doesn't just do visual control, but also does eye and hand method as well with it. What it'll do is take the information from the fruit detection node, so that'll be the input data, and what it'll then do feedback loop to update the robot control, so it's end effector. It's providing the information for the end effector for the robot control. So when it comes to the visual information, it can come from one or more cameras, depending on what you kind of want. But in this case study, it only uses one camera, which is located on the gripper. In this slide, you'll see the mathematics used for iron hand and visual servoing. As you see the equation, V is the output. So what V is something called screw theory kinematics. This is quite detailed and complicated. I will not go into this in this presentation, but it's very interesting to look at. You can find it on Wikipedia and other sites. But what you also see is S, which is the data which we'll be getting from the fruit detection node. That part is the eye and hand theory. For the visual servoing, we will be using pseudo inverse. That is the inverse kinematics. There will be more information on pseudo inverse in the next slide. So pseudo-inverse is a type of inverse kinematics which is normally used in visual control systems and is also used in the sweet pepper case study. So what it does, it's a solution to a system of linear equations that lacks a solution. So where you don't know where your endpoint is, it'll update over and over again to get to your endpoint. The solution is outputted as a matrix. So iron hand in conjunction with visual servoing has two types. So you've got single approach and multi-approach. Single approach will use an advanced algorithm or human to direct its path to your target using remote images taken or just by feeding it direct data. This can prove to be inefficient and not the greatest. The other approach is called multi-approach. So what it will do, it will scan the area, so take multiple images, and it will then find the best path towards the valid target. The downside on this, it does take a little bit longer, but is generally more successful. As you see, here's the maths for it down below. You can read it if you want to. Here is the flow chart for single approach and multi-approach. Single approach is on the left and a multiple approach is on the right. So the framework of this study is using something called finite state machine, or FMS. There are two types of finite state machines, Mori and Mealy. Morley is where the output of the state machine is purely dependent on the state values, and Morley is the output dependent on the current state values and the input values. Great thing about this is it's allowing to be flexible and reusable. Here is the flowchart of the finite state machine using this case study. I'll go through each state and what they do. The cold boot state is really simple. All it does is it gets the software and hardware ready. So for software, it'd be like if you're writing code in it, and hardware, it'd be zeroing everything down. So if it's stepper motors, you'll be getting it to 0 and just getting the whole machine ready. So the ready state is waiting for an external trigger, such as switch a button. In this case study, it uses a human to press a button for the ready state to go to the next state. So the function of the home position state is to, well, home your robot. The scan plant state, in the simplest terms, is multi-approach, what we talked about earlier on in the presentation. This will use the SLAM node, the image acquisition node, and the fruit detection node to map out the current area and going from waypoint to waypoint, taking images and detecting fruit from different angles. Depending on how from waypoint to waypoint, this can be done by putting a set of values such as your distance from plants and approach angle limiter. In this project, they use it at 90 degrees. After this process is done and the mapping is found, we'll then go to the servering state. So now in this state, I'll take all the information gathered in from the scanning state, such as the different approaches, and it'll use that to figure out which approach has the biggest viewpoint of the target, which is the fruit. From then, it will get ready to go into that waypoint position. Then it will move up very slowly. Each time it will take a picture, process it through the fruit detection, and then it will run iron hand and visual servering together to inch closer and closer and closer, each time taking another image, going forward, taking another image, going forward. After it's reached the target, it'll then pick up the target and move it all the way back and drop the target into a collection of some sorts. After that, it will then go back to a ready state. This state will only occur if there's any issues in the home position state, scan plant state, or visual serving state. An example of this could be it cannot find a target, or the visual serving has lost its target. So anything where the target cannot be found, or some random with servoing or the mathematics don't make sense, it will then return to a ready state, waiting for an operator or someone to do an external trigger to start all over again. So with this presentation so far, a lot of the material here can be taken into humanoid robotics, as the visual servoing and iron hand together can be used for reaching and grasping for humanoid robots in any settings, in a factory setting, a home setting, any settings that need to reach for something. Next item, which is really good, is the identifying objects from a household. So where we can detect the difference between different fruits and that, we can use this method to detect different things in a household, so medication, food, cups. This can be used for the elderly for moving stuff around. The third part is mapping pathways, so you can take the single approach or multi-approach. This can be used for construction sites, a lot of different movement. So you can take most of these aspects and apply it into human robotics really, really easily. So there are some issues with this case study. One is the ready state is that you need a human to well, do an external trigger to trigger the fruit picking machine. This can be inefficient and takes longer to do stuff. Another issue is cameras might not be optimized in certain areas. Yes, we are using iron hand method, which only requires one camera, but that won't get an overall visual of the whole area. So maybe having an external camera somewhere, and if a camera gets broken, it can cause issues. So I do believe that having multiple cameras, including one on the grasper, should be used. Future techniques to improve this current system is by using deep learning AI. So instead of replacing the fruit detection completely, you have another node that works with it, with AI. Maybe neural networking probably be best, as you can train it much easily. Reinforcement learning isn't really needed. You could do it, but neural networking with a lot of data and lots of images could actually help. Could also help with our pathways as well, with our multi-approach as well, so you can identify where the fruit actually is. So I do believe AI is extremely necessary to improve this current case study. Another technique is by adding additional stationary cameras to get a wider range of the area. That can also implement deep learning AI to identify targets, far more of them, giving the machine a better over image of the whole area. Here's the references and all the material that I used in this presentation. I'd recommend having a look at it. It could prove very valuable for different types of human robotics and just improving your overall knowledge.